This recording is going to cover an introduction to renal physiology as well as specifically addressing the process of glomerular filtration. Now, the formation of urine involves three major steps, and the first step is called glomerular filtration. Now, this step occurs exclusively within what we call the renal corpuscle. Now, the renal corpuscle includes the glomerulus, which is fenestrated capillaries, and Bowman's capsule. Now, the filtration is a process by which substances will leave the blood and go into Bowman's capsule, and what drives that is the high pressure that we have in the glomeruli. And we want a very high filtration rate because the kidney's major job, is to remove metabolic waste products such as uric acid and urea. So they need a very high pressure to remove these substances. And pretty much we'll go over specifically what can't be filtered, but you have your body fluids that are filtered or processed many times a day, and your glomerular filtration rate is about 180 liters a day, which is quite a lot. Now, the second process that is involved in urine formation is the process of tubular reabsorption. So substances that are filtered enter this renal tubule, and this is longer than what you see here. And things that are useful is we need to get them back into our bloodstream, because otherwise, if it stays in that tubule, it'll eventually be in our urine. And so we have a number of transporters that are associated with that nephron tubule, and that's going to allow us to reabsorb these useful substances back into the bloodstream. Now, the last step is tubular secretion. So tubular secretion is the process of which any substances that maybe we either did not get filtered or we need to get rid of some excess stuff is where things from the blood will go into that nephron tubule. Now, just as a reminder, around that nephron tubule, you have a lot of capillaries. They call them peritubular capillaries. And so substances from the blood there can, if we have specific transporters, is that we can secrete it from the blood into that nephron tubule. This is a way of getting rid of sometimes some excess hydrogen ions, or it's also a means by which we can get rid of excess potassium, and a lot of drugs are also secreted in this fashion. Now, the whole process we call excretion. So what's excreted is what's going to be eliminated in your urine, is a relationship. It's the amount that can be excreted is determined by what's been filtered, what's been secreted, and then subtract anything that's been reabsorbed. So any substance that has been filtered from the blood and not reabsorbed will be in the urine. Any substance that has been secreted, there's a specific reason why we're being secreted, is that will appear in the urine. Now, the kind of an overview here is, here's again the glomerulus, and you have blood coming in through what we call the afferent arteriole, and the high pressures that we have are going to allow we have a pretty high filtration rate that's going to enter that Bowman's capsule and eventually into that renal tubule. Anything that was not filtered is going to leave through the efferent arteriole. The substances move the nephron tubule. Anything that's not reabsorbed or substances that are secreted along that nephron tubule will be eliminated in your urine. And so the things that stay here in this tubule here, this will travel. And remember, a lot of this is out here in the renal cortex. So glomerular filtration takes place out here in the renal cortex. Number of portions of that nephron tubule are associated with that renal cortex. And what you have here, this would be referred to as initially the cortical collecting duct, because it's going to be traveling down the renal cortex that you see here. Then it's going to go down the medullary duct. And so you see here in the renal pyramids, we're going to have a lot of medullary ducts. So that urine will travel down there, eventually reach what we call papillary duct. And then at that tips of that renal pyramid, we have the renal papilla. And that urine is going to enter initially the minor calyx, plural would be minor calyces, then into our major calyx. So you got major calyces here, then into this area called the renal pelvis, and then out through the ureters. And then once it travels through the ureters, it's going to go into the bladder. Well, it's stored, and hopefully under the right appropriate conditions, the bladder will empty and it will leave through the urethra. Okay, so that's your elimination of urine. And just kind of, you know, in your notes, you do have all the different sections of the nephron tubule. I kind of skipped through that, but you have that the order in which substances are traveling through the nephron tubule. So what we're going to do is we're going to specifically address the process of glomerular filtration in this recording. Now, as I mentioned previously, the process of glomerular filtration occurs exclusively in that renal corpuscle. So that renal corpuscle, again, includes Bowman's capsule and the glomerulus. The filtration involves passage of materials from the glomerulus through these pores. Remember, the glomerulus, or glomeruli, which is plural for glomerulus, are fenestrated capillaries. So you have these pores in the endothelium. Well, they need to go through that, plus the things called filtration slits that we have here in Bowman's capsule, substance called the lamina densa, and then it will enter. You see all these little red dots here. These are some substance that had been maybe filtered from the blood. Now you'll notice some things do not get filtered from the blood. So the way this is set up is, again, those glomerular capillaries are fenestrated. Okay, so here again is that fenestrated. We've talked about those type of capillaries before. Is they're a little bit more permeable than continuous capillaries, but less than our sinusoidal capillaries. And they allow pretty much everything to be filtered from the blood except, and I'm going to go through more than, write this down, everything except blood cells, large plasma proteins, or anything bound to a plasma protein. And so the process of filtration is very relatively non-specific. So we have the things that we do want to get rid of, like metabolic waste, but we're also going to be filtering things like glucose and amino acids and stuff that I want to keep. We'll be filtering ions of various electrolytes. Some of that I want to get back. Some of it a little excess. I'm going to get rid of it. But so I need to be able to, when we talk about a little bit later, get the good stuff back. But right now we're just going to deal with the process of filtration. So what determines the rate of glomerular filtration? Now what you'll notice here is you see this filtration pressure is 10 millimeters of mercury. So how did we get it? And it's very similar where we talked about the Starling's law of bulk fluid flow. So we're going to kind of review that in a little bit. But first, let's just say what GFR is. And I'm just going to call it GFR. It's glomerular filtration rate. So it's the rate in which we're filtering the blood, and it's technically the amount of filtrate produced in the kidneys every minute. And here is the value. I don't have you memorize a lot of numbers, but this is one I would like you to be aware of. Is GFR is about 125 mils per minute. Now, how did we get it? It was very similar when we did the Starling's law of bulk fluid flow, in which you're determined do we have a net filtration or we do have net absorption, and then he had to take into consideration the filtration coefficient, which we used to address as that. And so let's just look at how they get that GFR. So you have actually before we do this, I'm just going to review this real quick. So we kind of bring it back to what we talked about before. Before we had, here's a blood vessel, and we talked about your capillary hydrostatic pressure, which tend to move fluid out. It was a filtration. It favored filtration. That's from your blood pressure. Then we also had something called your plasma colloidal osmotic pressure, and that was due to the presence of proteins in your blood, and that's going to favor absorption. So I'm going to just do red there. Then we also addressed the interstitial fluid. I'm trying to write it. I'm just going to write it like that. So interstitial fluid hydrostatic pressure. So you have fluid there in the interstitial space, and depending again how we used to write it is if I express it as a negative number, that would favor filtration, but if I expressed it as a positive number, that would oppose it. And then the other pressure we talked about is the interstitial fluid colloidal osmotic pressure, because you may have maybe some proteins in the interstitium, and that is a process that, actually let's go back and just do this one red so we can distinguish. That was a process that would favor filtration. So kind of review those, because then I'm going to apply them to what we're seeing now. So here in the red represents the glomerulus, and you have a glomerular hydrostatic pressure. So you have a pressure, a blood pressure within the glomerulus, and that, like the other one we talked about previously, that favors filtration. What you'll notice is this pressure is extremely high. It's 60 millimeters of mercury. When we did this for the systemic circulation, we said the average pressure for the capillary hydrostatic pressure was like 17.3 millimeters of mercury. So this is really high. So one thing before I move on, I want to explain to you why it's so high. One of the reasons is the afferent arteriole is much fatter than the efferent arteriole. So this here being constricted somewhat smaller than the efferent provides us high back pressure. So it increases the pressure here in the glomerulus. And another reason why that filtration or that capillary hydrostatic pressure in the glomerulus is so high is that the vessels in the kidneys are set up in what we call a series fashion. And if you set blood vessels, the arrangement up in series is that your resistance is much higher. It's cumulative. And so you have a much higher resistance relates to a higher pressure. And so you have this very large pressure, and that's what we want in the glomerulus. Now we have the capillary or the plasma colloidal osmotic pressure, because you have plasma proteins like albumins in that blood, and you see here the average, and it does not favor filtration, it favors absorption, is 32 millimeters of mercury. So here, this one's 32. This one is 60 millimeters of mercury. And then we also have in the Bowman's capsule, because this is what you're seeing here, is the Bowman's capsule, is you have a capsular hydrostatic pressure, because you have fluid that's being filtered in there, and that actually is a positive number, and you see, notice it opposes filtration, and it's 18 millimeters of mercury. Now what you'll notice is I'm not showing you any pressure for, in this case, it would be the capsular, or the equivalent would be the interstitial fluid colloidal osmotic pressure. I don't have that because it's 0, because we should not have any proteins being filtered. So that value is 0. And so if we look at these numbers, you have an outward pressure of 60, and we have two pressures that don't favor filtration. And if you add those up, you have 50. And so the difference between the two is you have a greater pressure that favors filtration. So the difference is 10 millimeters of mercury. And so we have a net filtration pressure of 10 millimeters of mercury, which is a pretty good value. Now what you'll notice is that in your notes I have the proper equation if you use the Starling's equation, but I can get the same value just doing it this way. But one of the things when you do these, in this case, the net GFR, is you have to take in consideration the filtration coefficient, which gives you an idea about how permeable, let's say, a vessel is. It tells you how much fluid will move across that membrane every minute per, whatever pressure that we have. And so we have a net filtration pressure of 10 millimeters of mercury. And what if I told you that the filtration coefficient in the glomeruli is 12.5 mils per minute per millimeter of mercury pressure difference? So what you end up with is 12.5 times 10, which gives us our GFR of 125 mils per minute. So we're filtering 125 mils every minute by our kidneys. Now, if someone actually does the math and you take in consideration there's 60 minutes in an hour, 24 hours in a day, you have 1,440 minutes in a day. You multiply that by GFR, you end up with 180 liters per day, and that's what I had mentioned to you previously. And so that's a pretty high amount. Now, the thing is, think about it. If we're filtering 180 liters per day, we better be getting some of that fluid back or we can be severely dehydrated. So just keep that in mind. We are going to get a lot of that fluid back because otherwise we would get dehydrated. So the urine output will vary, though, anywhere from like a half a liter, even depending on how well hydrated you stay, it can be up to like 20 liters a day. So it does vary depending on how well you're hydrated. So let's look at this table to look at things that could affect the glomerular filtration rate. And what you'll notice is I have everything that could decrease GFR. Just remember is if I switch the arrows on those determinants that can affect that GFR in that way, that would have the opposite effect. So we're just looking at things that could decrease GFR. So I'm just going to look at this top part real quick because these are more pathologic. So for example, if I decrease your filtration coefficient, your GFR would go down because, again, just look at the equation. So GFR is your filtration coefficient times that net filtration pressure. So if somehow you decrease this, and this, how would we do this is somehow you're damaging the glomeruli, or you're damaging components there in the kidneys, which can happen if people have poorly managed diabetes, high blood pressure, kidney disease. Those people are going to have issues with GFR, and to think about it, ultimately that can cause those people to end up having to have dialysis as a result of it. If you notice here, this abbreviation, the PB, stands for that Bowman's capsule hydrostatic pressure. So if you go back and look at the things that could, how they affect filtration. So here's that pressure. So remember, that opposed filtration. So if that pressure increases, that would decrease filtration rate. And the way that could happen is, say, if you have a kidney stone or some sort of stone that obstructed the urinary tract, and what will happen is things will back up and that pressure will be high, and that will kind of decrease GFR. And just think about, it's kind of a safety net. It's because, like, well, I can't get this fluid out, stop filtering because I can't get it out. Thing is, overall, though, that's not a very good thing because you still need to be able to filter your blood. This one also, if I increase that plasma colloidal osmotic pressure, since that is drawing or not favoring filtration again, that could also decrease filtration rate. There's things that could affect blood flow in the kidneys, or if you have increased plasma proteins. But these, I think, are the ones I usually think about the most. So I'm just kind of mentioning that, but I'd focus on these two besides that one. But the ones in the bottom of the chart is what I want to address the most. Is what you'll notice is if you decrease that capillary hydrostatic pressure, in this case the glomerulus, that is a major pressure. That's what really makes that filtration the way it is, because remember it's so high, is that could decrease GFR. And what are the things that could affect that? So you'll notice you have a list of different things. Is one of them is if your mean arterial blood pressure dropped. So if your mean arterial blood pressure dropped, that would obviously decrease that pressure in the glomerulus. Well, you notice it here, it says it's only a relatively small effect due to autoregulation. So let's address that. Let's look at that. Actually, instead of looking at that right now, this is a good time to stop. I'll have a subsequent recording that will specifically address the rest of these things that I have here, and also look at the role of the autonomic nervous system and hormones in regulating GFR.